how do we measure heat changes? We use something called a calorimeter to do this. And the heat released or absorbed by a system is related to two things: its temperature change and its heat capacity. Temperature change you already know about. What's heat capacity? Heat capacity is the proportionality constant between Q and T. Here's what it looks like. Suppose we have an object. The more heat an object absorbs, the hotter it gets. If we have a, let's say, a piece of steel that we want to heat up, and so we can bend it and so forth, we put it in a fire, and the object, the piece of metal, absorbs some heat from the higher temperature surroundings, and the manifestation of absorbing heat is its temperature goes up. So we could say that there will be a delta T for this process, and that delta T and Q are proportional to one another. The more heat the object absorbs, the greater delta T is. Or if we want to write it this way, we could say Q is equal to a constant times delta T. And the constant depends on what material it is that we're looking at, whether it's steel, whether it's glass, whatever it is. The heat capacity, which you may or may not be familiar with, is actually the proportionality constant right here for this object, and relating the heat that's absorbed by the temperature change. So we could solve this thing, this constant, we could call it heat capacity, is equal to Q over delta T. And this is for an object. Heat capacity of the object is determined by the heat change divided by the temperature change, and the units are joules per Kelvin. Okay, joules per Kelvin. Now, if the object is steel, that's one thing. If the object is carbon, it will have a different heat capacity. If it's glass, it'll have yet another heat capacity. Another way we can express heat capacity is, instead of per object, we could do it per gram or per unit mass. And when we do that, we use a lowercase c to represent its symbol. The specific heat capacity is the amount of heat needed to change the temperature of 1 gram of a substance by 1 Kelvin. Okay, so C is equal to Q divided by the mass in grams times delta T in kelvins. Now, in case you didn't notice it, back in Chapter 1, the Celsius temperature scale and the Kelvin temperature scale have degrees that are the same size. The Kelvin scale and the Celsius scale are displaced by 273 degrees. But the magnitude of the degrees is the same in both of them. So we could do this joules per gram per Kelvin or joules per gram per degree Celsius, and we'd still be all right as long as we're focusing on delta T. Delta T. It has to be delta T. Okay. A common specific heat capacity that we will encounter very frequently in the next week or two is that of water, 4.184 joules per gram per Kelvin. Worth noting, it'll save you time looking it up. Okay, now table 6.2 has specific heat capacities of some elements, compounds, and materials, so if you need to look one up for your homework, that's where to go. There are also more of them back in one of the big appendices in the back of your book. So, we want to learn now how to calculate the heat change Q from the specific heat capacity, the mass, and the temperature change. So this is the way it works. Q in joules is equal to the specific heat capacity, which we saw in the previous slide as joules per gram Kelvin, times the mass in grams. So that's going to cancel grams there. Grams will go out. Times delta T in kelvins, so the kelvins will cancel. And the answer will be in joules. So Q in joules is determined by taking the heat capacity from table 6.2, or maybe it's given in the problem, times the mass, which will have to be given in the problem, times delta T, which is T final minus T initial. So if an object has a temperature increase, delta T, T final minus T initial is positive, and the object gains heat, so that means Q has to be greater than 0. The object is a system, remember. Okay, so here is a problem that we need to work. How much heat is needed to raise the temperature of 45 grams of silicon from 25 degrees Celsius to 31 degrees Celsius if the specific heat capacity of silicon from the table is 0.710 joules per gram Kelvin. Okay, so this is the equation. We're going to calculate Q. We're going to put in each one of these values. We see the mass. This is the mass right here. 31 is the final temperature. 25 is the initial temperature, so the difference between those is 6 degrees. The constant, the specific heat capacity is 0.71. So the solution is Q is equal to C, joules per gram Kelvin, times the mass, times delta T, right? So delta T is T final minus T initial, which is 6 degrees Celsius, and since it's delta T, it's the same as 6 kelvins. 6 degrees Celsius is exactly the same as 6 kelvins, as long as it's a temperature difference, delta T. All right? So we plug, we chug, we check our units, and the answer is plus 192 joules. That's how we calculate a Q, if we know the amounts. Questions on that? All right. Now, in the laboratory, we do this using a calorimeter. And there are two kinds of calorimeter. There's a simple calorimeter that's built out of basically a styrofoam coffee cup. And then there's a more accurate calorimeter that's built out of a metal casing and some more complicated and expensive things. So, the constant pressure calorimeter is called a coffee cup calorimeter, or a cup calorimeter, all right? And calorimeters are used to measure the heat released by a process. Let's suppose the process is the following. We take a sample, which is a block of metal. Let's suppose it's zinc. Take a block of zinc, and we heat the zinc up to a known temperature. Usually this is done by putting the zinc into boiling water and keeping it there until it has the temperature of the boiling water. And then we take it out and put it into the calorimeter, which already has some water of its own at a known temperature and a known mass. Okay? Now, the sample, the zinc, is hotter than the water in the calorimeter. So, it stands to reason that heat's going to flow from the hot object to the colder surroundings. No doubt about that. Should be clear in your mind. So the heat's going to be lost by the system, and all that heat's going to be gained by the surroundings. So whenever you have, and I mean this every time, whenever you have a calorimeter problem, I want you to do, the first thing to do is to write down minus Q lost equals Q gained, because that's an expression of the law of conservation of energy, and it's always true. Minus Q lost equals Q gained. What's losing the heat? The system, the zinc, whatever it is. So minus Q of the system is equal to Q of the surroundings. What's the surroundings? It's the water, mainly. Now, I realize there might be a thermometer there and a few other things, but water gets most of the heat. So for a cup calorimeter, we will assume that every bit of heat lost by the system is gained by the surroundings. So in order to calculate Q of the system, we're going to calculate Q of the water, and Q of the water is given by the 4.184 joules per gram Kelvin, the specific heat capacity of the water, times the mass of the water inside here, and times the temperature change of the water, which of course you measure with the thermometer. So what you would do is measure everything before we put the zinc in, and that would give you T initial of the water and the mass of the water, and of course you know what C of the water is. Then after you put the calorimeter, the sample in the calorimeter, you stir it up until you get a constant temperature. That will be T final, okay? And then you calculate delta T times M times C, and you have your Q of the water. Now the only other thing you have to do to get Q of the system is to change the sign. It's beautifully elegant. Okay? So to finish up, to determine the specific heat capacity of a solid, you weigh the solid, which is a system, you heat it to a known temperature, which is the boiling point of water, you add it to a known amount of water at a known temperature in the calorimeter, you measure the final temperature, which is also the final temperature of the solid, minus Q lost equals Q gain, minus Q of the solid equals Q of the water, and we'll start there on Monday. Thank you. The other heat change that we are going to be interested in starting today is a heat change associated with chemical reactions. We showed the cannon that fired the cork out when HCl was formed from hydrogen and chlorine. That is a chemical reaction that generates heat. We will look at the characteristics of that type of heat change as well. And the last thing I want to remind you is the Q of the system, whatever the system is. If it's a physical object, it's Q of the object, or if it's a chemical reaction, it's the reactants and the products of the chemical reaction. Minus Q of the system equals Q of the water. In a simple calorimeter like this, we're assuming that the water absorbs all of the heat that's lost by either a physical or chemical process. When we get a little bit further into this, we'll look at a bomb calorimeter where we have a more precise instrument. But the principle's the same. Minus Q lost equals Q gained, minus Q of the system equals Q of the water. Q of the water equals the heat capacity of the specific variety, specific heat capacity of water, times its mass, times the temperature change. Now, in order to measure the specific heat capacity of a solid, like the geoscience student was measuring the heat capacity of a stone, a rock, a mineral, or something, you weigh the solid, which is your system. You heat it to a known temperature, as would be true if we put it in boiling water. We add it to a calorimeter, which contains water at a known temperature and of a known mass. Then we stir it and wait for the temperature to come to equilibrium. We measure the final water temperature, which is also the final temperature of the solid when everything comes to equilibrium. Again, Q lost is equal to Q gained. So we can write down the expression for the specific, the Q from the object in this case, or the system, and the Q of the water, which is what heats or what absorbs the heat. So minus Q of the solid equals Q of the water. So we'll plug in for that C of the solid times the mass of the solid times delta T of the solid, which is the final temperature minus the initial temperature. That's minus Q of the solid. Q of the water is C of water, 4.184 joules per gram Kelvin, times the mass of the water, times delta T, again, T final minus T initial. If you want to solve this for the heat capacity of the solid, that is over here. You divide both sides by the mass of the solid times delta T of the solid, and this is the expression you get. You can either memorize this, or you can remember how to set it up. If that's better for you, either way is okay with me. But there is a negative sign right here, and I don't want you to forget that. Very important that you remember that negative sign is there. C of the solid is equal to minus C of the water times the mass of the water times delta T of the water divided by the mass of the solid times T final minus T initial, delta T of the solid. To cement this in your memory, let's do an example of determining the C of the solid. A 55-gram piece of metal Z was heated to 99.8 degrees Celsius and dropped into 225 grams of water at 21 degrees Celsius in a cup calorimeter. The final temperature was 23.1 degrees Celsius, and that applies to both the metal and the water. Okay? Now, I want you to remember that delta T in kelvins has exactly the same value as delta T in degrees Celsius. They're the same size degrees, so you won't forget that, right? The mass, it's good to set up a table, as we said before. The mass of the metal is 55 grams. The mass of the water is 225 grams. The initial temperature of the water is 21 degrees Celsius. The initial temperature of the metal is 99.8 degrees Celsius. And the final temperature for both of them is 23.1 degrees Celsius. So our equation, to remind you, is C of the solid. So this will be C of Z is equal to minus sign times C of the water, which is 4.184 joules per gram Kelvin, times the mass of the water, 225 grams, times delta T of the water. This will be the final temperature, 23.1 degrees, minus the initial temperature, which is 21.0 degrees. And then we're going to divide that by the mass of the solid, which is 55 grams, times delta T of the solid, which was 23.1 degrees, minus 99.8 degrees.
Is that backwards?
No, it's not backwards. This is T final minus T initial. And this is T final minus T initial. The water, T final was higher than T initial, so the water got warmed up. The metal got cooled down by the water. And notice that this term here is going to be a negative term. And so this minus sign is going to cancel with that minus sign, and that's a good thing because all heat capacities are positive numbers. And when I plug this in, I have, well, let me just write it out, minus 4.184. I'm not going to put the units here since I did put them up here. This is kelvins and this is kelvins. 4.184 times 225 times 2.1 divided by 55 times minus 76.7. The two minus signs will cancel, and C sub Z I calculated to be positive 0.469 joules per gram Kelvin. Okay? Specific heat capacity is has units of joules per gram Kelvin. Questions on this calculation? So this is how you can determine the specific heat capacity and then maybe the identity of an unknown piece of metal or other substance of some kind. So, how to find Q of reaction. In a cup calorimeter was placed 50 milliliters of 0.5 molar sodium hydroxide solution at 25 degrees. Then 25 milliliters of 0.5 molar hydrochloric acid at 25 degrees was added. Now, of course, a base and an acid are going to react. Acid-base reactions are typically exothermic. And sure enough, after the reaction had finished, the temperature had gone up from 25 degrees up to 27 degrees. So that's a clear indication. It's an exothermic reaction, and we have to determine Q, and they want it in kilojoules. Okay, they want Q in kilojoules. So T final for both of them. Well, for everything inside the calorimeter is 27.21 degrees Celsius. T initial for the solutions that were used was 25.00 degrees Celsius, and so the difference is 2.21 kelvins. 2.21 kelvins. Okay? And the mass of the water, or solution, it is a solution, it's not pure water, but the mass of the solution, we will assume that it's dilute enough to have the same density as water. So 50 milliliters would be 50 grams, and 25 milliliters would be 25 grams. So 50.0 plus 25.0 grams is 75.0 grams of solution, or H2O. Okay, now minus Q lost equals what? Q gained. We always start calorimeter problems thinking that way. Something lost the heat. In this case, it was a chemical reaction that lost the heat, and the water, the solution, gained it. Okay? So the heat was gained by the water, so we'll say it was equal to minus Q of the water. And if we can determine, it's not minus Q, it's Q of the water. Minus Q lost equals Q of the water. And of course, that's going to be C of the water times M of the water, the mass of the water, times delta T of the water in kelvins. Okay, so that C of the water is 4.184 joules per gram Kelvin, times the mass of the water is 75 grams, times delta T is 2.21 kelvins. And when I did that arithmetic, I got 639 joules, to three significant figures, but it wants it in kilojoules, so we're going to go ahead and just convert it to kilojoules, 1 kilojoule being equivalent to 1,000 joules. And so the answer in kilojoules is 0.639 kilojoules, which is equal to Q of the water. Okay, now what is Q of the reaction? It doesn't say what's Q of the water, it says what's Q of the reaction. So we have to go back and think about this for a minute. Minus Q of the reaction is Q lost, so that's equal to Q of the water. So Q of the reaction is equal to minus Q of the water, which is equal to minus 0.639 kilojoules for this amount of reaction. However much reaction occurred, it gave off 6.639 kilojoules. Questions on that one? Yes, go ahead.
When you're talking about water, do you mean the water as in the water in the calorimeter or the contents of the reaction?
There was no extra water in the calorimeter in this case. We just took 50 milliliters of one solution, mixed them with 25 milliliters of the other solution. The water that's in those solutions is the water that we're talking about. It's the water that absorbs the heat. That was a good question. Thank you. I should have made it more clear. Other questions on this one? That's Q. Now, in order to get from Q to delta H, we have to figure out how many moles of reaction occurred. It's an acid-base reaction, right? So we'll have to write the equation for it and figure out how many moles of product formed. Now, have you got a picture in your mind what the products are of sodium hydroxide and HCl? solutions? Who has a good picture of what they are? Sodium hydroxide and HCl. I combine them. One of the products is going to be water, or what's the other one? Salt, sodium chloride. Okay, so what we need to do is to figure out what the net ionic reaction is. And of course, for an acid-base reaction, we already looked at that. It's H plus OH minus goes to H2O. And then figure out how many moles of H2O we form. Okay, I am ready to start the second part. Does anybody have any other question about this part? Remember what Q is because we're going to use it. How to find delta H reaction. This is a commonly missed kind of question because students will read this as Q. And delta H reaction doesn't have to be equal to Q. It may or may not be. But delta H reaction is equal to the Q of the reaction divided by moles of reaction. I'm sorry, you can't read that, but I'll write it down here again. So this is the same problem exactly, except it's asking us for something different. It's asking us for delta H. So delta H of reaction, I'll write it bigger here, is equal to Q of reaction, which we already know, divided by moles of reaction. It's kilojoules per mole. That's always the units of delta H. So kilojoules per mole. So let's write down the equation. It's sodium hydroxide, aqueous, plus HCl, aqueous, goes to sodium chloride, aqueous plus water. And the net ionic equation is OH minus aqueous plus H plus aqueous goes to H2O liquid. And the number of moles of hydroxide ion is 50 milliliters times 1 liter over 1,000 milliliters times 0.5. And I think I wrote that down somewhere. That is 0.025 moles of hydroxide ion. And water, or I'm sorry, HCl, there's half the volume of that solution, 25 milliliters instead of 50. So it's going to be half the number of moles since the molarity is the same. So this is 0.0125 moles of H+. So as we look at this, how many moles of reaction will there be? How much water will be produced? It's a limiting reactant problem, isn't it? We have to figure out, since we're given amounts of these two, and it's not specified to be in the equilibrium equimolar stoichiometry here. So we have to look at this and see which one of these will produce less water. And I think you can see it's H plus going to produce less water, and we don't even have to do any calculations. There's going to be one water for every H plus, and so that's going to be 0.0125 moles of reaction. We judge that by the number of moles of product formed, and we know acid react with base completely. Are you comfortable with that so far? How did I get the moles? Volume converted to liters times moles per liter. Other questions? All right. Then we're ready to plug into delta H. Delta H of the reaction is equal to Q of the reaction divided by the moles of reaction, and that's equal to negative 0.025 693 kilojoules. It wants the answer in kilojoules, so we'll keep it there, divided by 0.0125 moles of reaction. Is it 639? Is it really? Check this on the calculator. Well, I have it written down here as 693, and I think that's right. So if I said 639, would you please make that correction? Sometimes my tongue gets tied up, doesn't know what to say. 693, I believe, is the correct number. Okay, so when I did that math, I got minus 5.54 times 10 to the fourth, sorry, back up, 5.54 kilojoules per mole. With the negative sign right there, don't forget that. So delta H of reaction, when things go bad, they go bad in a hurry. Obliterate everything over to there. It's minus 5.4 kilojoules. I apologize for making the error. Per mole. 55.4 kilojoules per mole negative. It's an exothermic reaction. And this is moles of water formed, or moles of reaction, whichever way you'd like to call it. All right, sorry for the big blotch out here. 0.693 kilojoules over 0.01 ends up being 55.4. Somebody want to check it for me? Sometimes I can't be trusted. Now let's suppose that we wanted a more accurate measurement. We could use something called a bomb calorimeter to measure, for example, heats of combustion and so forth. A heat of combustion could actually be Q of combustion for a variable amount, just however much material we put in here. This thing works. This is a bomb inside of the calorimeter, and then we have a metal shell which contains the water and the stir and the thermometer and an electrical igniter here. And so if we wanted to know what the heat of combustion of, let's say, some new kind of margarine, we'd put it in here, weighed amount of it, and set up the calorimeter, and then fill it with pure oxygen, an excess of pure oxygen, and then start the reaction going, measure the temperature change that's involved, knowing the heat capacity of the water present and the heat capacity of the calorimeter as well. Accurate work you've got to correct for the amount of heat absorbed by the calorimeter. So minus Q of the reaction is equal to Q absorbed by the calorimeter and Q absorbed by the water. And if we want to measure the delta H of combustion, the delta H of a combustion can be measured as well, but in that case, we have to figure out the number of moles of reaction. Pardon me. So what we're going to do here is to, first of all, talk about what Q of the calorimeter is. The calorimeter is an object. And at the beginning of our discussion of heat capacity, we said the heat capacity of an object is the temperature, it's the proportionality constant when you do temperature is proportional to heat change here. So this Q of the calorimeter is the heat capacity of the calorimeter, which has to be calibrated. You have to measure it with known heat source, usually electrical, times delta T. So again, delta T is going to get us this term. And Q of the water is going to be the same Q of the water we saw before. C of the water times the mass of the water times delta T. Now, one thing I need to say before I leave this is that this is a constant volume experiment. As such, delta H does not apply because delta H requires constant what? Pressure. Constant pressure. I heard someone say it. So this is constant volume, and when you have a constant volume situation, the heat change is delta E, not delta H. But fortunately, in many cases, delta H and delta E are almost the same, so it's not a big deal. Now, bomb calorimeters are used to get nutritional information. Do we have any nutrition students? Anybody want to raise their hands? Nutrition students? Okay, well, everybody knows, I think, that if you pick up a can of beans, you can look on the can of beans and see how many calories are in that bean, right? Everybody's seen that. Where do you think that information came from? Well, of course, it came from one of these. The beans were burned, a certain amount of them were burned, and the heat change was measured, and that is different from what happens when you eat the beans, but the heat change is the same for the two. So that's the calories. The only difference being those calories are capital C calories, which are equal to a kilocalorie of lowercase c. Calories, nutritional calories, are 1,000 times larger than scientific calories. So let's take this one. We have a 1 gram sample of octane, and it was burned in a bomb calorimeter containing 1.20 kilograms of water at 25 degrees. The final temperature went up from 25 up to 33.2, so that's 8.20 degrees or kelvins for delta T. See, the calorimeter is 837 joules per Kelvin, meaning if you put in 837 joules, the temperature will go up 1 Kelvin. Okay, what is the heat of combustion, Q in this case, in kilojoules per gram of C8H18? Well, that's going to be easy because we started with exactly a gram, so all we have to do is solve for Q, and Q will be, when you think about Q for a second here, remember it's Q of the calorimeter plus Q of the water. So minus Q of combustion is equal to Q gained. Minus Q lost equals Q gained. That's equal to Q of the calorimeter plus Q of the water. Okay? Now, M of the water is 1.2 kilograms, which is what? 1,200 grams. Has to be in grams. And delta T is 33.2 minus 25. It's 8.20 kelvins. And that's for the calorimeter and the water, for both of them. Okay. Let's see here. All right. Now, minus Q of the calorimeter, is the first term, and that's going to be 837 joules per Kelvin times delta T, which is 8.20 kelvins. That's the heat absorbed by the calorimeter. Plus the heat absorbed by the water is 4.184 joules per gram Kelvin times 1,200 grams times delta T, which is 8.20 kelvins. Okay, did I do that right? I think so. And if you do the arithmetic, I haven't rounded here yet, 6863 joules absorbed by the calorimeter plus 41,171 joules absorbed by the water. which is equal to 48,013 joules total, produced by burning 1 gram of C8H18. You see what a good fuel that is? Produce a huge amount of heat. 48 kilojoules per 1 gram. That's why we use it for a fuel, and why we're going to be hurting real bad when it's gone. And it will be gone in your lifetime. Not mine. Okay, so a minus Q of combustion, get off the soapbox, Geanangel, is 48,013 joules. Now, the last thing we need to do is to convert it to kilojoules. So 48,013 joules times 1 kilojoule per 1,000 joules is 48,000. I'm sorry, 48.013 kilojoules. Now it does say that it wants this thing in kilojoules per gram, but what if it had said it wanted delta H? What would you do? If it wanted delta H, we'd have to take Q of combustion and divide it by moles of C8H18, right? And we've got Q of the combustion here is minus 48.013, and we would have to then divide that by the number of moles of C8H18. It's 1 gram times, this is 114 grams per mole, so 1 mole over 114 grams. And when I did that one, I ended up with minus 5.48 times 10 to the third kilojoules per mole. Okay, didn't ask for that, but if it did, that's how you would get it. Common fuels are hydrocarbons and coal and wood and things like that. Fuels for organisms are mainly fats and carbohydrates. And these molecules have carbon-carbon bonds and carbon-hydrogen bonds, and when they undergo combustion, what happens to them? The carbon-carbon bonds break and form carbon-oxygen bonds. The carbon-hydrogen bonds break and form carbon-oxygen bonds and oxygen-hydrogen bonds, CO2 and water. Now, it's instructive to think for a minute about the magnitudes of the delta H for these things, because if you think about it in any terms that are sort of make sense to you, let's suppose that you're a marathon runner, okay? And nobody ever told you what to eat before the marathon. You're going to run 26 miles, is that what it is? Your body's going to consume a large amount of energy. So let's suppose you have a choice in what you're going to eat, let's say in the day before the marathon, right? And you might eat some material which has oil in it, fried chicken, okay? It's got lots of oil in it. Or toast with butter and peanut butter. And ethane is representative of those kinds of oils in its composition overall. So I'm going to do as simple a thing as I can here. I'm going to look at the heats of combustion, both in kilojoules per mole and kilojoules per gram, of a representative of the oils and fat family and the octane family, if you will, and we just call the C2H6. And by measurement, the delta H combustion in kilojoules per mole is negative 1,560 kilojoules for 1 mole of ethane. Ethane's one of the components of natural gas. Well, that's a whole lot of energy for 1 mole. 1 mole is only 26 grams or 30 grams, something, not very much. If you express it in the unusual way of kilojoules per gram, it's about negative 52 kilojoules per gram. Now let's suppose that we look at the ethyl alcohol here, ethanol, as a representative of the kinds of foods that already have some carbon-oxygen bonds. This only has one. If you look at sugar, there's a lot more, or carbohydrates. So we put in 1 oxygen in a carbon-hydrogen bond. It goes right there, right? And look what happens. It drops from 1,560 kilojoules per mole down to 1,367. Now, if you look at this, this is also like comparing octane as a fuel or gasoline as a fuel compared to ethanol as a fuel. Now, you know, we are, as a society, using a lot of ethanol in our gasoline, at least 10% by law in most cases, and some places as high as 85%, in order to make the air pollution effects, mainly, as small as possible, keep our air clean. Well, that's a good thing, but notice per gram that we go from negative 52 kilojoules per gram to about negative 30. So if you use ethanol as a fuel, a very high percentage of your gasoline, what's going to happen to your mileage? What's going to happen to your acceleration? It's a good thing, but it has some less than desirable aspects to it. All right? Now, if we look at some of the fuels over here, foods instead of fuels, here are some of the fats I was talking to you about. Vegetable oil is 37 kilojoules per gram compared to 52 for ethane. Margarine is about a little less. Butter's a little less. And we go back to carbohydrates and think about our runner. Table sugar has about half the kilojoules per gram. And rice has a little less than that. And maple syrup has a little less than that. So it really looks like carbohydrates, even though if you don't exercise, they'll put plenty of pounds on you if you eat too many, only half as much as fats. So if your objective is to keep warm, if you're an Eskimo or somebody who lives in a very cold climate, you're better off with fats than you are carbohydrates. But nonetheless, it's a heck of a lot of energy that our fuels have. So have a look at this. That's a gummy bear sitting there. And I'm going to show you this little thing. It's a very famous little video clip that I've used for a number of years about what happens when you get the energy out of the gummy bear as fast as possible. We're going to drop the gummy bear into liquid potassium chlorate, very high temperature.
If we combine 1 gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. And in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product favored.
Yeah, I know. You want to see it again.
If we combine 1 gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product favored.
So even carbohydrates, which suffer by comparison to some fuels and foods, have a tremendous amount of energy in them. Okay? Now let's look at this question then. A dietetic dessert is claimed to have less than 10 capital C calories. That's dietary calories. Okay? 10 dietary calories. And the question is, by measuring the heat of combustion, we get a certain number of data coming out of it. And one serving is burned in oxygen in a bomb calorimeter, heat capacity 8.151 kilojoules per Kelvin to test the claim. The temperature increases by 4.937 degrees Celsius. Is the claim correct? So we're going to calculate the heat gained by the calorimeter. And in this case, this kilojoules per Kelvin number includes the water that's in the calorimeter as well, because you don't see any citation for how much water is there. So the water is included in this. Minus Q gained equals Q lost. Minus Q lost equals Q gained. Minus Q of the reaction equals Q of the calorimeter. Q of the calorimeter is the heat capacity of the calorimeter times delta T, which is 8.151 kilojoules per Kelvin times 4.937 Kelvin. That's 40.24 kilojoules, which of course is, this is 10 dietary calories, it's 10 kilocalories, and this would be 41.84 kilojoules. So this, in fact, 40.24 is less than 10 capital C calories. So that's how these things are made. Okay, these numbers. Okay.